Good morning, children. So, we move ahead with the topic isomerism in coordination compounds. So, this topic is very important to understand the geometry or the shape of the coordination compounds. So, let us first understand what do you mean by the term isomers. So, isomers are all such compounds which have the same molecular formula. So, since they have the same molecular formula, they are going to have the same chemical properties. But their arrangement of atoms is totally different. But here, when I talk about the term atom, we mean to talk about ligands. So, ligands are arranged in different ways around the metal atom, which gives rise to these isomers. So, let us understand about the different types of isomerism which is exhibited by coordination compounds. The first one is structural isomerism, okay? And the second one is stereoisomerism. So in this video, I'll be only talking about structural isomerism and stereo, which is again subdivided as geometrical and optical, will be captivated in next video. Fine, let us understand about structural isomerism. As the word itself suggests, that means there is a difference in their structures. So these isomers differ in their structures, but they have the same molecular formula. And why is there is a difference in their structures, or structurally I can say they are very much different from each other? It is because of the different arrangement of ligands around the metal atom. So points to be highlighted over here, I'll just highlight they differ in their structures although they have the same molecular formula, and that is because atoms align in different orders. Fine. Now let us understand about different types of structural isomerism. The first one to highlight is ionization isomerism. The word itself suggests you something related to primary and secondary valency, because in Werner's theory we understood that primary valency is ionizable, right? Primary valency is ionizable, whereas the secondary valency is non-ionizable. So since there is a concept of ionization here, that means we can easily understand there is some exchange between the primary and the secondary valency. To put in simpler words, there is an exchange between the counter ions, which are the primary valencies for you, and the ligands, which satisfy the secondary valencies for you. Fine here. So I'm going to highlight it for you here. See here, form of isomerism because of the exchange of counter ion and the potential ligand. This can be understood with this example very well. If I ask you to write the name of this complex, I think you should be able to do that. Let me give you here the name of this. First, we are going to write about the ligands because it has here the primary valency. Before citing the nomenclature, I should find out the charge on the complex. So the charge comes as plus on the complex because bromide ion has -1 charge. Now let us write the nomenclature. That's pentamine, right? Penta because it has 5 molecules. Then this is another ligand, but it is anion. So its name should end with O. And we know it's known as sulfate in common language. So we are going to use sulfato. Okay. The name is sulfato. Then comes the name of the metal atom, that's cobalt. And after that we have to find the oxidation state. How to find the oxidation state? We have learned many a times. Let me keep it as X plus amine is 0 into 5. and then sulfate is -2, the charge, equal to +1. So what is the value of X you're going to land up? It's +3. So this oxidation state is written in Roman number as 3. So that's the name of this complex. Now, if you want to find its ionization isomer, how will you do that? There is an exchange between the primary valency and the ligand. So bromide ion enters inside the complex as a ligand, and sulfate moves out as a counter ion, which can be observed here very well. So that's the ionization isomerism. Let us go ahead with hydrate isomerism, which is another type. The word hydrate is related with water. That means water over here is acting as a ligand. And I told you before, water cannot be used the term for ligand. It's aqua. So whenever water is used, in this case, we have to restrict to the term called as aqua, which can be seen in this example over here. Yeah. Now here I'll highlight water is acting as a ligand, and how many molecules of aqua are there? That's 6. Chloride ions are acting as the counter ions. But when we talk about hydrate isomerism, what actually happens? This water molecule, which acts as a ligand, comes out in the form of counter ions. So here water molecule is taken as a counter ion, and one of the chloride ion enters inside the complex as ligand. So again there is an exchange between the ligand and the counter ion, but we have to be very specific which ligand got exchanged with the counter ion or the primary valency is water molecule. Okay, and remember, just a minute over here to write H2O like this. Fine. So that's about hydrate isomerism. Next we are going to talk about linkage isomerism. So in linkage isomerism, there is something which is getting exchanged within the complexes. So when I say exchange between the complexes, you can understand here it is more about the ambidentate ligand. So ambidentate ligand, try to just recollect what did we learn for ambidentate ligand. I'm going to highlight it here for you. Ambidentate ligand. If you remember, I gave you example of nitrito, that is NO2. Nitrito can be used as an ambidentate if it coordinates with metal atom with nitrogen atom, right? It was mentioned like this in the video, and it can also coordinate with oxygen atom, in which we are going to write it like this. Oxygen coordinating with metal atom. Fine. So there are two different coordinating atoms over here. One is nitrogen, and the other one is oxygen atom. So that's what is highlighted over here in linkage. Linkage means there is something which is happening within the ligands. So ligand, the ambidentate ligand, if it coordinates with O, it's one type of isomer. On the other hand, if it coordinates with N, it's the other form. So these are the two linkage isomers of the isomerism. Fine. So this is all done, and remember, in this I should highlight it for you so that you don't forget. It's only talking about ambidentate ligands. The next one will go ahead with coordination isomerism. So coordination, the word itself, that means there is an exchange between the complexes itself. So here we have a combination of complexes. You can easily understand here, I'll highlight it for you. This is one complex, this is another. So it's a mixture of a complex. That means there is no concept of primary and counter ions, right? And the complex. Now, when two complexes associate and their ligands get exchanged, such type of isomerism is known as coordination isomerism. So there is an exchange of ligands between these two complexes. It is very well evident in these examples. So I highlight over here inter-exchange of ligands, and of course it's the cationic and the anionic entities. So we are done with it. Yeah. Now the next important concept is about homoleptic and heteroleptic complexes. These two terms are very, very important because the entire stereochemistry, that is the stereoisomers, are discussed with the help of these two terminologies. So when I use the term homoleptic, what do I mean? Homo means same, and lepticity is related with the ligands. So all such complexes which contain only one ligand, one kind of ligand, they are classified as homoleptic. So I'll underline here for you complexes which contain only one kind of donor atoms. Donor atoms means I'm talking about ligands. And here this example will make you very clear that the ligand over here is cyanido, only one type of ligand. Wherein when we talk about heteroleptic complexes, the word hetero means different and lepticity is related with ligands. So very clearly all such complexes will have more than one kind of ligands. So I highlight here more than one kind of donor atoms. That's the ligand. Example, if you can see, you can understand it very well here. Here I have amine as one ligand, one type of ligand, and chlorido as another type of ligand. So such type of complexes are called as heteroleptic complexes. Next, we'll be talking about stereoisomerism in next video. So learn all these concepts well and also practice nomenclature again. Thank you all.